In the last lecture, we saw basically two uses of symmetry. One was almost trivial, where we had a field that was complex, had two components, and we saw that basically we get two particles that don't speak with each other, but they are conserved not only the total energy or the total number of particles, but also each type as itself. And we saw that we can get the same result from observing that this Hamiltonian has a symmetry, which is adding to this complex field a phase. And we saw that that also leads to the same conservation. Then we moved to a bit more complicated symmetry. And we basically required that gauge symmetry will be conserved. By gauge, I mean adding a phase to the field, to this complex field. But not a global phase as we did in the first case, but a phase that can change at each point or time. And then I stated, without showing it, that of course the previous Hamiltonian doesn't fulfill this symmetry, but if I add an additional field, something with four components, we called it a four vector, then I can fulfill this symmetry by adding a few terms to the Hamiltonian. And I said that this new Hamiltonian or Lagrangian, doesn't matter, fulfills the symmetry. I stated it without proving it. What I'll do in the first part of today's lecture would be to show that indeed it fulfills that symmetry. In the second part of the lecture today, I'll completely shift gears. We'll leave fields until further on in the course and do something that is known as second quantization, a terrible name to a very nice concept. And once we'll get there, I'll explain why we need it and why it's so popular, especially, let's say, in condensed matter physics. Okay. Now, someone mailed me this morning about where in the textbooks we have today's lecture. So sorry for not answering. I wasn't at a place where I had access to the textbooks, so I couldn't. If you want to know where you can read about the next lecture, please mail a couple of days ahead. Okay, so let's sum up where we got at the end of the previous lecture. We had three fields, phi and phi conjugate. We added an additional field, a mu, and we wanted to do this following in which is changing the field by multiplying it by a phase, but a phase that depends on x and t, not a global phase. Okay, these are the shifts I'm doing to the field and the phase. Okay, and the Lagrangian. Okay, and the only additional definition that I need is what is this F mu nu? Okay, all this we defined in the previous lecture. Now I said if I'll replace phi and all and a in this Lagrangian, I'll remain with the same Lagrangian. Now I should prove it. Okay, let's do it term by term. Okay, I have here 4 terms. And we'll start with the lie-lowing fruit. This guy. Well, this is basically trivial. So, just for completeness, so I have to write down the transformed fields. Okay, this obviously doesn't change by the transformation. Let's move to this term. So I'm transforming it and prime means I'm putting in this definition of transformation into the definition of the tensor. Okay. Okay, this part of the exercise is a bit tedious, but nothing special about it. And just looking on this term, I'm always reminded from a joke that Feynman told, well, not a joke, a story that he told in his book, Surely You're Joking, Mr. Feynman, when he is arriving a day late to a conference somewhere in North Carolina. And he's stepping out of the airport, steps into a cab and tells the driver, well, take me to the university. So the cab driver tells him there are two here, which one of them? So Feynman said, the one that yesterday you took all this bunch of nerds all the time mumbling mew, 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 mew during the whole trip. So we have a lot of news, but it's fine.
זה אמור להיות פלוס.
Indeed. Thank you. Okay, so just have written down the definition. Nothing clever, just opening up what's written here. Okay, let's see what we have here. Immediately, the order of derivation doesn't make any difference.
Sorry, in line 3, it's free tag. The first line, little up, upward. בשורה 3, כאילו, ביטוי 3.
Theta has not.
בשורה הראשונה על הלוח. It's in the beginning free tag, right tag. Why it's tag?
That's exactly what I'm doing. I'm now proving that under this transformation, the Lagrangian is symmetric. So I'm performing the transformation. Just straightforward. Every place that is written theta here, phi here, I'm putting the transformation. That's all. Same here. And as you can see, basically, I'm remaining with the same. So, fine. Okay, so I'm left with the first two terms. So, okay, just performing the transformation, taking the definition and seeing what I get. Okay? Again, just replacing phi and a by phi prime a prime and writing down.
The exponent is supposed to be with a plus sign.
Indeed. Okay. So let's start with that. Performing the derivative. Both theta and phi could depend on x, y, z, or t. Okay, this is just this guy.
So there's no minus sign in the beginning.
No, okay.
Okay. Plus, now it's a simple multiplication.
I think you're also missing phi in the beginning, in the first term.
Indeed.
That's right.
This way.
Okay.
Yeah. Okay, something disturbs me if it's a plus or minus, but in a moment we'll check it out. New, do, new. Okay, and let's write the second term. Okay, the same game.
Should it be upwards, the indexes?
Yes, the index should be up. Should. Write down correctly. Okay, the same game. Okay, now let's see what is my problem. I'm going to fix it. Okay, so doesn't seem to work, and the reason is one small mistake here. I'll define it the other way around. Otherwise, I'll have to change the derivative. Nothing more. Okay, so here, well, it will change this, but won't change anything else. Okay? Here, of course, nothing changes because we don't use this definition. Here, the only thing that changes is this guy.
What did we change before?
Hmm?
What did we change in this word?
In 3, just phi is going to be in minus IQ, and phi in complex conjugate of phi goes to plus. Just a matter of definition. So as I said, in 3, all it doesn't change anything. In 4, it doesn't change anything. Here's the only thing that in the first line changes is this to minus. And here this changes, and all these guys. And here this changes to plus. This changes to plus, and basically then we remove all the minuses. So
The last line in 1 should be minus for the minus IQ, right? Because it's the derivative.
No,
this guy,
Yes.
it's not a derivative.
It came from
The
It's
first
just
one.
this times this. This is plus.
Ah.
Okay. The first term is a derivative, the second term is just a simple multiplication. Okay, and this whole exercise has the purpose of that the first and last term cancel each other. I could leave you with the same definition of plus and minus and changing the definitions of the derivatives. That would have been the same thing, but let's keep it this way. Same here. Okay. Now I'm pulling out Okay, just the two remaining terms I'm pulling out e to the power I q theta. And now, when I'm multiplying one by the other, I lose the phase. And they remain exactly with first time, second term. Okay. So, as I said in the previous lecture, I just want to re-emphasize it. You actually know this this Lagrangian from classical electromagnetic. This term is just a free field. This term is a correction to the basically to the momentum in the classical sense. You remember, instead of P, I have P minus QA, IQA. And, well, this term, nothing happened to it. That's just the mass just doesn't change. And you basically obtained here the quantum field theory, Lagrangian, of a particle. This is not an electron, for the simple reason that we have only two terms in the complex field. And as I told you in the previous lecture, you need actually 4 to describe a spin half fermion. Well, this is the spin 0 boson, the phi here. But in principle, the same building stones you construct from you can construct QED out of it. And this guy has the additional advantage. Someone can tell me what is the additional advantage of this Lagrangian?
Upon what?
Upon Lagrangians that we previously considered.
Shows interaction.
We have interaction between two different fields, which is the electromagnetic field and a particle field. And of course it obeys special relativity, because Maxwell equations obey special relativity. And as you can see, it's simply symmetric in mu and u, which tells you basically it's okay, fulfills special relativity. Okay, so as I told you, that's as far as we get at this part of the lecture of regarding fields. Basically, you have now the knowledge to write down a simple non-interacting field, free field, and solve it, as we did in the previous lectures, and get the spectrum, an eigenfunction of this problem. More interesting would be getting something beyond boson fields and getting something which will also enable us to take into account interactions. You don't know yet to solve this type of problems, and hopefully we'll get to that towards the end of the course. Yes?
Where do we see the interactions in the Lagrangian?
You have an A field and a phi field, and they're multiplied. Now, we will go into it in more details towards the end of the course, but it's a good question, and I want you to look actually what's written here. Okay, basically you have here A mu right? And derivatives of it, all kinds of three field operators here with the phi field always appearing as 2 and A appearing as 1. Now, without knowing anything, it actually tells you what happens in this interaction. And how can I see it? Let's do the Fourier transform, changing it into creation and annihilation operators. So basically, in this guy, you'll have terms of the form AK and AK prime, because you'll have your summations over K and K prime. And here you'll have another term of the type of B. I'm writing to differentiate between creation and annihilation operators belonging to A and phi. I'm writing those that belong to phi as A and those who belong to A as B. Without knowing anything, basically you see what these interactions do. I annihilate a particle with K prime and create it back as a particle with K. Meaning, this particle, which is not an electron, but let's think about it as an electron, changes its momentum. Very reasonable for interactions for a particle colliding with another particle. Okay. This is stranger. We have only one term. But what does that term tell me? I had a certain number of particles of this A field at Q, and one of them was annihilated. What happens here? That's the interaction you all know and love. And a particle collided with a photon, swallowed it, and came out with another momentum, another energy. The opposite will be this particle just delivers a photon, gets out another photon, adds a photon to the system, and changes its momentum. Now, the details, the spectrum, conservation of energy, and all that is built into this Lagrangian. But the basic building blocks of this type of interaction is already here. The fact that I have a multiplication of three fields. If I had here an interaction between two particles that don't annihilate one another, so I would have here an additional term that says I'm annihilating at Q, creating it at Q prime. And I would have to write a Lagrangian to handle energy conservation. in this type. But that's interaction. Interaction is basically a particle is destroyed in some properties and recreated with a different set of properties, and by doing it, it's doing it by interacting with another particle that also something happens to it. For a simple photon, it's just either created or annihilated. For more complicated particles, it could have a more complicated term. Okay, and actually the problem that we will solve will be adding a 5 to the 4th interaction, which means two particles are coming in at k and q and coming out at k prime, q prime. That's the simplest interaction that one can think about without adding a new particle into the game. Okay, actually we'll see similar things now coming out from a different formulation of the many particle problem. And that's known as second quantization. And now, basically, second quantization is created for, let's say, in general, simpler systems than these fields. When I say simpler, what do I mean? I'm assuming that these systems, I have no creation or annihilation of particles. So the only thing that can happen is that a particle changes its properties, but it's still there. And I don't care even about special relativity. I'm assuming that my particles are moving much slower than the speed of light. So now you understand why it became very popular in condensed matter, because most of the electronic properties of matter, electrons don't have enough energy to annihilate or to be created. You conserve the number of electrons is the problem. And the relative velocity, their velocity is not relativistic, or the corrections are very small and no one cares about them. Okay, what do I still care? I still care about the basic property that I have 10 to the 23 electrons in my piece of metal. So I can't just write the Hamiltonian for a single electron and be happy with it. Actually, to be more precise, in any problems that I have more than one electron, I have to worry about it. So I can go through life solving the hydrogen atom very happily without knowing anything. But the hydrogen molecule, already I'm in a problem. I have to write the many particle wave function of this system. Electrons are identical particles, therefore I have to treat them accordingly. And the basic idea of second quantization is coming out of the good old definition of single particle systems to reformulate it for many particle systems. Okay, so to understand the basic idea, I'll just start with the simplest systems that we can think about, two particles. This.
You said that in a solid state you don't have creation or annihilation of particles, but
Of electrons.
of electrons.
Phonons, photons,
Yeah.
What's not, you have creation and annihilation. If you really are bothered by it, you have to go to field theory. If you just replace them by some classical average, which is done in a lot of cases, and in most cases it doesn't make any difference, happily you can continue. Okay. So, as I told you, the name is confusing and not informative. We're not doing the second quantization. I think that towards the end of this lecture you'll understand from what is the logic behind this name, but it would have been much better to choose another name to the procedures that we're doing here. Okay, you start from a single particle. Okay, the whole undergraduate course actually dealt with how to, perhaps not the whole, but a large portion of it dealt just with solving this type of problems. Let's assume that we have a single electron problem that we know exactly how to solve. From my point of view, all I need to know is the spectrum and the eigenvalue and the eigenvectors. Okay. Now let's assume even something simpler. I want to put in two particles into the system, and my only and they don't talk with each other. Okay, when I say that they don't talk with each other, it means that one is not interacting with the other, but am I exact in saying that? Someone can tell me when it's exact and when it's not exact? Perhaps I'll remind you that there are two types of particles: bosons and fermions. For bosons, completely exact. For fermions, well, I don't interact directly, but if a state is occupied, if one of these states are occupied, the other particle can't also be in that state. So, in essence, we do have some kind of interaction. So, but let's say it in the following way: I have a Hamiltonian that doesn't express directly interaction between those two particles. Okay, so what am I supposed to do? Well, simple. Each particle sees this. If it would have been a single particle, it would have sat at a given eigenvector of this problem, have some eigenvalue, and that it doesn't, and it completely doesn't care what the second guy does. If it's a boson, and if it's a fermion, it cares only as much as don't sit in the same state. Everything else is the same. Okay. So, basically, a state of the system would be particle number 1 is in state lambda 1, particle number 2 is in state lambda 2. This is the Hilbert space of this problem. You see that the size of this Hilbert space has grown. Previously, let's say I had a single particle problem with n different eigenvalues of size n. Now I basically have something which is for bosons n squared. Fermions it's a bit smaller because I can't be in. Now okay, if that was all that was involved here, life would have been very simple. What am I missing in just writing this guy? Something that we discussed in the first lecture of this course. When I'm writing this eigenstate, or wave function,
Degeneracy?
a bit connected, but degeneracy, let's say for fermions, doesn't exist, right? So first of all, you can say you didn't remove your states where lambda 1 is equal to lambda 2, but and that's a problem at the moment. But I have a bigger problem, a deeper problem. And the problem is this statement of particle 1 is in lambda 1 and particle 2 is in lambda 2, I can't state it because I don't know who's particle 1 and who is particle 2. Therefore, I basically have to write something that will look exactly the same for the opposite case. For particle 1 in state lambda 2 and for particle 2 in state lambda 1. Because there's no way at all that I can, there's no way at all for which I can distinguish between those two states. If I can't distinguish, the wave function can't distinguish. So how do I do it? I specifically write the two different possibilities. Where here, now the order became important. That's particle 1 in state lambda 1, particle 2 in lambda 2, and the opposite. Particle 1 in lambda 2 and particle 2 in lambda 1. What is this strange Z?
It's fermions or bosons.
Okay, so I give the same weight to the possibilities that 1 is in state 1 and 2 is in state 2 to that 2 is in state 1 and 1 is in state 2. And actually, at this point, I also put in that fermions can sit in the same state. Because if lambda 1 is equal to lambda 2, I'll have here a minus and it will be 0. I don't have such a state. Why do I have only bosons and fermions? Because there's no other ways that I can build this wave function except for by plus or minus in between. Okay, that's great for writing down a wave function of 2 particles. Well, we need a wave function to the 10 to the 23 particles. Okay, so let's say I have n large n particles. Okay, so what is this monster? So it's telling me a very simple story. Write all of the permutations. The row here are permutations putting my end particles into these different states. I'll have, if I'm dealing with fermions, I'll have to write here some law how to put, if to put +1 or -1 for it. And for fermions, life is easy here because it's just in factorial. If we have bosons, I have to take into account, let's say, if I have two different degenerate states, not to count them twice. So this is this part. Now, you should see it once in your life. And are there any chemists here?
Why do you ask?
Because I'm going to insult them. And if you're not a chemist, that will be hopefully the last time in your life that you are seeing. Why? Think about it. 10 to the 23 different permutations. How can you work with it? And why chemists still work with it? Because they have some problems with a small number of electrons on a molecule or whatever. 4, 6, 8 electrons, and you're still able to write all of the permutations. So, if you heard the term Slater determinant, unfortunately or unfortunately, we have better ways to deal, and we never sit and write down this wave function because it's just impossible to work with it. Perhaps in very old textbooks of the 40s and 50s of condensed matter physics, you sometimes see this notation. Since the 60s, 1960, you don't see nobody working directly with this language. Nevertheless, nowadays, take a chemistry textbook in quantum chemistry, you'll see a lot of Slater determinants stuff. They don't like the second quantization language, and they think it's complicated. Actually, you pay a small price to learn it, and you save a lot of effort after. Okay. So, basically, if I have these states, any states that I'm writing here actually hides this mega permutations that I have to put in. But if I write down any state, any many particle state, how does it look like? Basically, I'm writing down. Tell me how many particles I have in the first single particle state. Tell me how many particles I have in the second, and so on and so forth. And I forgot here something.
It's the population in each state.
Yes? And I'm giving an amplitude to this state. The only thing that I should demand to use the same end. This is confusing. Yeah.
What is beneath the first sum? Yeah,
Okay,
the second line. The second line.
Just a moment, let me. Number. Okay, I have to give you, if you remember, that's exactly the solution that we got in field theory. Let me know how many particles do I have in state 1, 2, 3, okay? Let me know the amplitude of the wave function on this state. Normalize. And I'm ready to go. I'm not so ready to go because to translate this to this language is not direct. I have to know the permutations and so on. Okay, but at least I understand what I'm stating here. Questions about it. This is extremely important because at the end of the day, in second quantization, that's the basic notion.
You said that there is k particles, right?
No,
There is
K
n
states.
particles.
K states.
Okay, so in each state of the case, it's like n2 for saying. It's n2 represents the number of particles.
in the
That's-
second state of the single particle,
What is the meaning number of particles in single particle state?
let's say I have a particle in state 27 and a particle in state 15. So I'm giving you, okay, to make it simpler. Uh, okay. So,
I mean, like
wait a minute.
that's the case for fermions. If like in some point we insert 5, what does this mean?
Bosons.
Yes, so there is n particles in single particle state. Yeah, that case. So there is 2 particles in n2 state.
Yes. The
It's a
only
single
difference in
energy
this
level.
language between fermions and bosons, define it, please.
Yes, so it's an energy level. That is the meaning.
It doesn't have to be an energy level. It could be an energy level.
Okay.
I could decide that I want to describe it by any operator, basically, right? Could take momentum and tell you how many particles are at this momentum and how many particles are at that momentum. Which, and we'll learn, probably not in this lecture, how to transform from one single particle base to other. But this is general. Choose a single particle base. I don't care which one you choose. Probably if you choose something that is inconvenient, you'll have problems to solve this problem. But from the point of view of description, no problem at all. Whatever single particle orthogonal base that you choose, you can give them any particle description. What I need, this seems as child's play. I'm just exchanging notations, right? What I'll need is a way to write the Hamiltonian and a way to operate to do something with the Hamiltonian in this language. And here actually comes in the term second quantization, although it's not second quantization. All it tells you, look, how to express, okay, before that I want an additional definition because I need it. Basically, I've written a state with n particles, right? What happens if I want to add electrons or subtract electrons from the system?
Depends on
I'll have to have some way to go from n to n minus 1 or n plus 1. So for n particles, we have the usual Hilbert space. This is just saying that we have the usual Hilbert space. And now I'm saying I combine all the possible spaces with 0 particles, 1 particle, 2 particles, infinite number of particles, and it has a name Fock space. From your point of view, it's the same as Hilbert space, because in the end of the day, if I'm looking on a system and I don't know the number of electrons in it, so the summation over all possible states in Fock space still has to be 1. It's either in a state with 0 electrons, or 1 electron, or 2 electrons, or whatever number of electrons. Okay, so yes.
So can if a particle is in a superposition of 2 states,
Mm-hmm.
then you write half in one state and half in another one, or the coefficient?
1 over square root of 2, and yes. 1 over square root of 2 just to.
So whenever you measure the system, if with a large number of particles, they are always in a superposition, because you don't measure one, you measure the whole system. So
Well, depends. Let's say, take a chunk of metal, don't connect it to any external leads, and measure, I don't know, the total charge or whatever. You'll have a fixed number of electrons. It can't leave there. On the other hand, connect it to leads in a circuit, then it could have superpositions of number of electrons, because you can catch it at the moment that an additional electron went in or left. You don't know. So the answer is depends. The same idea that in statistical mechanics you have a Gibbs ensemble or a fixed number of particles ensemble. It depends on your setup. Okay. Why do I need all this gymnastics, defining Fock space and so on? Because I want to build a way to build these states without going into these definitions. I don't want to see these definitions. So what do? And basically,
What about the distinguishability?
excuse me?
You said earlier when you wrote the lambdas, because you can't distinguish between the two particles, you have to write the superposition. So here, if you have two particles in the same state, you don't distinguish between them when you write it like that.
Okay, let's wait with it. Because I'll define now a way to manipulate and do each calculation without bothering with all these permutations. The point is, of course, when I'm writing the state behind, there are different permutations. So I label it, this is a representation of something with different permutations. And then I'm saying I want to do all my mathematical manipulations without caring about it. Okay, otherwise, I couldn't do anything. Let's start with the only state I don't have to worry about permutation. And that's the state where I have 0 particles. vacuum. Define an operator. I'm taking an operator, AL, bigger. It tells me create a particle at state L. Okay, what does it mean? Okay. Hence the term second quantization. Why? Let's go back to the harmonic oscillator. We had a classical system, we did quantization, and we got that basically we have a set of creation and annihilation operators that work on some Hilbert space, telling me how many quantas of energy do I have in this oscillator. Here, basically, conceptually, a similar case. I'm creating a particle with a certain quanta at a certain state. That's why they called it second quantization, because I'm working on a quantized one particle system and adding creation and annihilation to it. That's not second, just that terminology. Okay, these are not the same thing. Annihilating on state L where I had a particle, I go to the vacuum. Annihilating a state that didn't have anything there is just not defined, equal to 0. This is a state, this is just 0. Now, what we will do is look what happens when I'm using these operators for a state that I have already n particles in it. See how the conditions for fermion and bosons are actually fulfilled. For example, that fermions, if I'm trying to create a state in a position, to create a particle in a state that has already a particle in it, will lead to 0. While for bosons, everything is fine. I'll just get 0 n plus 1. That will have to do with some conditions, different conditions on how A and A dagger behave for fermions or bosons. And basically, I would like to know how to, if I have an operator, how do I calculate, how do I write an operator in these terms? And how do I perform a calculation? Let's say, how do I get an answer on how many particles do I have at a state, or what's the energy of that state, or what's the momentum of the state? And all of this comes from translating the single particle definitions into this language. Okay, and that we'll do in the next lecture.
ריצ'רד, אפשר שאלה? אז אם אתה מתייחס לאלקטרון, כביכול אתה, כאילו אתה כן יכול לרשום הרי 2 באותו מצב.
לא, אלקטרון? לא.
למה? אבל אם אתה מכניס ספין...
אז אני צריך, אז פה אני אצטרך להגדיר אלקטרון במצב ספין מסוים. אני אצור אותו, הבסיס החד חלקיקי יהיה בסיס חד חלקיקי של נניח K, של ערכים עצמיים של התמה, ובאיזה ספין נמצא.
אז כאילו זה יהיה יצירה כביכול של ספין.
של אלקטרון במצב K עם ספין חצי. בדיוק כמו כשאת פותרת את משוואות שרדינגר, כשאת מכניסה פנימה ספין, את צריכה להגיד האם זה ספין אף או ספין דאון. גם פה את צריכה להגיד, את יוצרת ספין דאון, ואם זה אלקטרון, אז כמובן אם אני יוצר, כבר יש מישהו עם ספין אף, לא ייכנס, אם יש מישהו עם ספין דאון, זה לא מחלט במצב אחר.
אז הוא אומר מה אנחנו רואים פה.